Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the second lecture of our module 8 where we are discussing about the breeder reactors. We already had one lecture and I personally feel I was quite awful in the second part of that lecture as I was feeling a bit exhausted and drowsy and just went through the motion. So, probably I would like to clarify some of the topics which I feel I have not explained clearly, at least in the latter part of that second lecture. But what we have done so far is we have discussed about the concept of breeding. Breeding refers to an example which is shown here. This kind of reactions we term as breeding, where a fertile isotope or a fertile nucleus consumes one neutron in a non-fission capture reaction, that is like an N gamma kind of reaction, where it absorbs a neutron. So, thereby produces another isotope of the same one, like uranium 238 in this example is capturing a neutron and producing uranium 239 plus gamma radiation. But this uranium 239, as we have seen, has an extremely small half life and therefore, almost instantaneously it gets converted to neptunium 239, that also has a quite small half life, something in the order of 2 days. Therefore, it also undergoes another beta decay to finally produce plutonium 239, and plutonium 239 is a fissile isotope. So, we started with a fertile isotope of uranium 238 and after one step of neutron capture and 2 steps of beta decay, it gets converted to a fissile isotope. This particular kind of reactions are called breeding, and breeding is an extremely important concept from nuclear reaction or nuclear reactor operation point of view, because if you think that uranium 235 is the only fuel that we can use in nuclear reactor, then our option is quite limited. Of course, among naturally occurring or among all the fissile isotopes that we can visualize, uranium 235 is probably the only one which is naturally occurring, and isotopes like plutonium 239 or uranium 233 or a few others can artificially be produced by virtue of such kind of breeding reactions. But suppose if the power generation is dependent only on uranium, then we know that the uranium ore that we get from the mines contains only about 0.7% uranium 235 and rest is this uranium 238, which is fertile in nature. And therefore, if we have to depend only on uranium 235 for power production, we are going to utilize only 0.7% of what we are going to get from the ore, or I should say maximum of 0.7%, because there will always be some kind of practical loss, some portions of that U235 itself also will remain unutilized, etc. But because of this option of breeding only, that 99.3% of uranium 235, which till this chapter was looking almost an useless kind of thing, that actually can be very useful, because while it goes through those neutron capture reactions, maybe in the resonance absorption zone or maybe in the thermal neutron zone, that can get converted to plutonium 239, thereby producing or adding some more fuel into the reactor. That means, we are loading the reactor with just uranium 238 and 235, and uranium 235 is the only fuel. If it is just loaded with natural uranium, we are having only 0.7% of the total mass acting as the real fuel. But as time goes on, of course, there will be depletion of uranium 235 because of the fission reaction, but there will also be depletion of uranium 238 and that will lead to the formation of this new fuel, that is plutonium 239. So, breeding can lead to this conversion of fertile isotope to fissile isotope, thereby adding some new fuels or developing some new fuels into the reactor. In fact, in modern day thermal reactors which are fueled purely with uranium, there as much as 30 to 40% of the total power production may come from plutonium 239, because Pu239 is an extremely fissile isotope with significantly high fission absorption cross section, and also the power that we generally harness from one fission reaction of Pu239 is slightly higher than what we can get from U235 I should say. There can be quite a few other kinds of fission, other kinds of breeding reactions also, like we have shown through this diagram in the last lecture. I am just repeating once. Uranium-238 generally can have only one kind of nuclear reaction, which is this neutron capture leading to uranium-239. Now, U-239 and Neptunium-239 both have extremely small half life, and so therefore, we can just neglect them, and just we can consider that U-238 can directly get converted to Pu-239, which is a fissile material, and it also has, as shown here, it has a 64% probability of participating in fission reaction. Therefore, its fission cross section is reasonably high, but it can also participate. There is 36% probability of having a capture reaction, that is Pu239 after capturing a neutron in 36% of the total cases can go through a N gamma reaction producing Pu240. Now, Pu240 is also a fertile material, and it again has just a single probability of neutron capture and conversion of Pu241, which again is a highly fissile isotope. It has 72% possibility of fission, but it can also participate in couple of other reactions, like there is 25% probability of a neutron capture reaction to produce Pu242. There is also about 3% probability of having a beta reaction to produce Am241, but these are generally less fertile kind of isotopes, and their half lives are quite small as well. But there are possibilities that this Am241 can go through another neutron capture reaction by producing M242M, which is a highly fissile isotope, and it has 84% probability of participating in a fission reaction. This way we can see almost a chain kind of reaction. Like another very important part of this chain is that this Am242, which let me erase this Am242 which is appearing here is a very short lived isotope with extremely small half life, can go through a beta decay to produce this curium-242, which can participate through a series of reactions to finally get converted to Cm240, first Cm243 and then Cm245, both of whom are extremely fissile isotopes, extremely active, and generally these are the two isotopes which are primarily considered for nuclear weapon fabrication. So, both of them are extremely important. Another possibility of this Cm242 is to go through a alpha decay, thereby producing this Pu238, which again being a fertile one in nature can participate in neutron capture to produce Pu239. So, we are back where we started. It's a, therefore, you can clearly see it's a whole net. We are starting with U238, and then there are different kind of possibilities of getting different kinds of fissile nucleus formation through breeding. How many fissile nucleus we can see in this net? Like Pu239 as number 1, then we can find Pu241 as the other one. These are two different isotopes of plutonium. We can also see this curium-243 and 245, and in some cases we can also have this American 242M. So, there are 5 different fissile isotopes which we can get just by this U238 participation in breeding reaction, and therefore, though we are having only uranium-235 initially as the only fissile nucleus, we can have 5 more in the nucleus, with plutonium-239 being the most common one for the obvious reason, because that is the direct product of this uranium-238 breeding. And as the fraction of uranium-238 is so high, 99.3% in case of natural uranium fueled reactors. So, there is a very high percentage of plutonium-239 also can be found in the reactors. But the most important thing that comes out from all these concepts of breeding is that By virtue of this breeding reaction, a nuclear reactor can produce its own fuel, or the portion of initial supply, that is uranium 238, which is not a fuel, a reactor can convert that to a fuel, thereby adding some more fuel to the originally supplied one. And also something I shall be talking about later on, after the reactions are over, whatever is left with, say once we have operated the reactor for a long period of 1 or 2 years, then the spent fuel that is left with, that also can contain significant amount of plutonium and also a small fraction of uranium 235, which can again through some kind of reprocessing can be fed back to the reactors, nuclear reactors. Therefore, even the waste material can also be used as fuel. The so called waste material can act as fuel for nuclear reactors. And I hope these terms or this whatever I am saying, that sounds familiar to you, because this here if we can make this breeding reaction or make proper use of this breeding reaction, the total duration over which the same fuel can be used is enhanced by a large amount or significantly large amount. For getting, suppose you have a reactor which is giving you 1000 megawatt of power output. Now, if we want to get that same 1000 megawatt only from uranium 235, then we have to supply a significant amount of fuel, but only because of this production of plutonium in course of the reaction, we can supply much less amount of initial fuel and still attain the critical condition. That is the total critical mass requirement that definitely reduces because of the breeding. And also in the very first lecture, I have mentioned under the while I was talking about different advantages of nuclear power, I have mentioned the term renewable, and this is where nuclear energy can be renewable. Quite similar to the conventional renewable energy like solar or wind, it can produce its own fuel and thereby the supply of fuel can be almost infinite. Just to put that in context with plain uranium based reactions, if we are considering only uranium 235 as the fuel, uranium being a metal which is found in normal ores, its total life is not very high. Like if we consider the present, if we take the present day electricity consumption or power requirement over the entire world as the benchmark, then present stock of oils and natural gases may last only about 30 years, whereas present stock of coal is expected to last something like 50 to 70 years. If for uranium 235 or just natural uranium, I should say, if we are depending only on that, then this nuclear energy also is expected to last only something like 70-80 years, because after that probably the stock of uranium will get exhausted. But we can use this breeding technology to produce more fuel, thereby reducing the consumption of natural uranium. And proper use of this breeding technology, a projection shows that the total life of the same uranium which we presently have can be something like 30,000 years. So, that definitely is a remarkable figure to use. And also another fuel, that another kind of breeding reaction that you have seen in the previous lecture, thorium 232. Thorium 232 can absorb neutron and produce uranium 233, which is again an extremely fissile isotope. And thorium stock at the world at the present is at least 3 times more than uranium. So, thorium will definitely be lasting much more compared to uranium, and we can produce this uranium 233 from thorium, thereby getting a very long supply of fuel almost over an infinite period of time. So, renewable energy from that point of view can also be treated as a, or I should say nuclear energy from that point of view can also be treated as a renewable source of energy, because it is near infinite, or 30,000 years for the moment we can also definitely consider to be an infinite period of time. Now, moving further, we have discussed about the breeding or conversion ratio, which is defined by this C, and it is defined as the ratio of number of fissile isotopes available through breeding divided by the initial number of fissile isotopes which are consumed during the reaction, and that can be related to the thermal fission factor and the total leakage by relation like this. Here one thing I would like to add with our previous discussion, C is generally called the conversion ratio, and as we have already seen, depending upon the value of C, we can call a nuclear reactor to be a breeder, a converter or a burner. When the value of C is greater than 1, then we call that a breeder reactor, because then it is able to produce its own fuel. And then instead of using the term conversion ratio, the term breeding ratio is used. As long as C is less than 1, like in case of burners and converters, we stick with the conversion ratio, but when C is greater than 1, that is when we are talking about breeder, we call it breeding ratio. We have discussed about breeding gain and doubling time. Doubling time is the time required to double the number of fissile nucleus that is there. For common thermal reactors, the doubling time is something approximately of 10 years. So, the doubling time is in a way is an indicative of the reactor producing the fuel for another reactor. Means we have supplied some amount of fuel to get the reaction started, and after this doubling time, something like that 10 years are over, then there will be enough fuel stored inside which is sufficient to run 2 reactors. So, half of that can be taken out of the reactor and we can start another reactor for this. So, the doubling time is also very important to know, at least from the operator point of view. The role of eta we have discussed, and we briefly discussed about the open and closed fuel cycles. This is where I went through the motion a bit, and I would like to come back here again. So, to start with, we have this, which is the fuel cycle or the nuclear fuel cycle. There you can see there are several steps here. The first step, of course, is the mining. The mining from here there refers to the harnessing the uranium from the core of the earth. Now, uranium is a very common metal, and it is present in most of the rocks and soils, also in many rivers and even in the sea water also. And the ore that we get generally from the mines contains 0.3 to 20% of uranium. So, that is quite large range. But of course, here we are talking about the natural uranium, that is whatever we are getting from the ore, 0.03% or 20%, whatever, only 0.3% of that is uranium 235. There are principally 3 kinds of methods of mining which are shown here. It can be the in situ mining or in situ harnessing, the mining from the depth of the mines, or also the heap leach technology. Now, uranium actually is a quite abundant metal, about 500 times more abundant than gold, and something very common metal like tin has nearly the same kind of abundance as uranium. So, getting uranium, at least at the moment, is not very difficult. There are several sources or several countries where uranium is available, the largest producers being Kazakhstan, Canada and also Australia. These are the countries which are the largest contributor in total uranium stock of the world, but there are several other countries where uranium is available. Once we have got this raw ores from the mines, then we need to go through the milling process. Milling refers to the ores that we have harnessed from the mines, they are crushed and they are also chemically treated to separate out the uranium from whatever else was there in that ore. Generally, the milling sites are located very close to the mines, because the uranium ore that we get from the mines, that is very mildly radioactive, but still that should be considered very carefully, and operator should be cautious. That is why generally it is not allowed to travel, or that ore is not allowed to travel long distance before the milling process is run. We do it quite close to the mines itself. And then the result of that milling process is something known as the yellow cake. It is actually an yellow powder of U3O8. Uranium can have several chemical valencies, accordingly it can have several kinds of oxides. U3O8 is just one of them. And from the milling process, the principal product is this yellow powder of U3O8, which conventionally is called the yellow cake. And the uranium concentration in original ore, where it was just 0.03 to 20%, through this milling process it can be raised something more than 80%. Quite often in the common mills it can be generally in the range of 90% or more. So, the yellow cake that we have found, which is U3O8, that contains more than 80% uranium. Next is the conversion step. Conversion refers to the conversion of this U3O8 to UF6. uranium hexafluoride, which is actually a gaseous material. So, UF6 is, after this conversion, UF6 is filled in large cylinders and allowed to solidify, and then the cylinders are loaded into metal containers and shipped to the plants, or generally if some other enrichment or some other kind of chemical processes are required, it is supplied there. So, what we are getting at the enrichment location is this UF6. I repeat, UF6 is a gaseous material, where the U3O8 that we are getting from the milling plant, that is an yellow powder. Next comes the enrichment. Enrichment is an extremely important topic in nuclear power generation, because we have already discussed in an earlier module about the thermal fission factors, etc. And from there you know that as the fraction or percentage of U235 in the uranium increases, thermal fission factor also increases. When in natural uranium, where we have only about 0.3% of U235, the thermal fission factor is something like 1.36, and with increase in enrichment, that increases rapidly, and around 18 to 20% of enrichment, it more or less saturates to something like 2.05 or 2.06. So, it is and as the thermal fission factor increases, overall multiplication factor or reactivity of the plant also increases, and hence the power output also keeps on increasing. And enrichment is also a quite controversial technology, because this is generally, while the major processes of enrichments are quite standard, but exactly how that is done or exactly how those processes are controlled, those are quite complicated technologies, and every country has their own process and generally likes to keep that as a secret. Very few countries properly can enrich the uranium fuel, whereas other countries who do not have the technology, who doesn't have the technology, but still are running nuclear plant, has to go for either natural uranium or export that from some other countries. So, the term enrichment definitely refers to increasing the fraction of uranium 235 in the fuel, something like this. In natural uranium, it is only about 0.7%. So, the natural uranium ore that we get, or even after the milling and conversion steps are done, whatever uranium we are getting, that is natural uranium only, which contains only 0.7% of U235. And because of this enrichment process, we can increase the fraction of U235 to whatever level we would like to have. Common thermal reactors use enrichment in the level of 3 to 5%. In fact, it can be quite low, like 1.5 to 2% as well in PWRs. But pressurized heavy water reactors, I hope you remember, does not use enriched fuel, because it uses deuterium as a moderator, which has near 0 absorption cross section, and therefore, it can go for natural uranium. But PWRs or BWRs uses ordinary water, and water has a small absorption cross section. So, some portions of the neutrons will get absorbed. To increase the probability of fission occurrence or neutron nucleus interaction, we need to go for some kind of enrichment, which is generally limited to 4 to 5%. But that is in thermal reactors. When we are talking about fast reactors, we need much higher level of enrichment, because I hope you remember the fast fission cross section or the cross section fission cross section subjected to fast neutrons are extremely low for all common fissile nucleus U233 or U235, compared to their thermal fission cross section. Fast fission cross sections are quite small, and therefore, we need a high neutron density, high neutron flask density to achieve the fast reactions or fast fission, and that is possible only when we can increase this number of U235 isotopes in the total fuel. Generally, the power reactors or industrial reactors uses an enrichment of the level of 4 to 5%, whereas research reactor can go up to 20%. But in case of fast reactors, just what I was talking about, it is not just 4 to 5%, it can be quite high, something in the range of 10 to 15% or even 20% in some rare cases. And for nuclear weapons, we need even larger enrichment, which can be well above 80%, can be in the range of 90 to 95% as well. So, depending upon for what purpose we are trying to go for enrichment, we have to decide which level we are which level or which kind of applications we are focusing on. There are several ways we can handle or we can have this enrichment, but almost all of them utilizes UF6. The advantage of fluorine is that it has a single naturally occurring isotope. Therefore, whenever we are dealing with UF6, generally all those enrichment procedure focuses on separating uranium 235 and 238, and their chemical properties are virtually the same, because the number of protons in both the isotopes are same, and it is the number of protons, that is the atomic number, which determines the chemical properties. But as the number of neutrons are different, that is U238 nucleus has 3 more neutrons, so it is slightly heavier, and that small difference in mass is the one on which this enrichment technology or separation technology is based on. Now, if fluorine has multiple kinds of isotopes, then it will become very difficult to identify the difference between two UF6 molecules are coming because of the difference in fluorine or difference in uranium. But thankfully, fluorine has just a single naturally occurring isotope, and therefore, whenever two molecules are having different weight, we can clearly say that the heavier one contains U238. And another advantage is UF6 is gaseous, and so we can go to very high temperature levels, which are generally required for the enrichment process. This is the way UF6 is produced during that conversion process. First, that U3O8 that we are getting in the form of that yellow cake, that is treated with hydrogen to form uranium oxide, UO2, uranium dioxide I should say, and that UO2 is then reduced using hydrogen fluoride to get UF4, which further reacts with fluorine to form UF6, and that UF6 gas is then taken to that enrichment plant. These are the 3 methods of enrichment which are the most popular one. Gaseous diffusion is the older technology. Initial enrichment procedures were based upon the gaseous diffusion only, but nowadays it is becoming almost obsolete in the favor of the gas centrifuge. The biggest problem in gaseous diffusion is it is extremely costly, or it requires extremely high level of energy, which is significantly smaller in this gas centrifuge process. In fact, an estimation shows that the amount of energy consumed during gaseous diffusion can be as much as 45 to 50 times larger than what requires in a gas centrifuge with equal amount of output. Now, coming to the technology, in case of gaseous diffusion, we generally use a membrane, a porous membrane. Now, uranium 235 atoms being lighter and also more active, they are more likely to move around in the container and strike with the walls, and whenever they strikes that porous membrane, it can cross that permeable membrane. So, there is a larger probability of uranium 235 to cross this membrane compared to uranium 238. But of course, just one step of membrane is not sufficient, rather a diffusion process can involve a few hundreds, maybe more than 1000 number of such membranes, all having same dimensions, sometimes small difference in their nature, but ultimately what we get is on one side of this membrane or group of membranes, we have the original fuel, or I should not say original fuel, rather on one side of the membrane we get enriched fuel, on the other side we get the depleted fuel. Here enriched means the one which contains more uranium 235 than the natural one, whereas the depleted one refers to the one which contains less amount of uranium 235 compared to the original one. So, the diffusion process is associated with or it is based upon the lighter uranium 235 showing larger activity and thereby crossing the membrane. In case of gas centrifuge, we use a centrifugal action, that is as the centrifugal force is put into the action on the UF6 made gas through a spinning centrifuge, the uranium 238 or the molecules containing uranium 238 being heavier, they will move closer to the walls, whereas uranium 235 containing molecules are more likely to stay close to the center of the centrifuge or centrifugal force. And therefore, if we collect the gas close to the center line, there will be a much higher fraction of uranium 235 compared to uranium 238. So, the enriched stream will come out collected somewhere very close to the center of this centrifuge, whereas the depleted stream is collected from the edges of the container towards the or near to the wall of the container. The third one, laser enrichment. Gas centrifuge, by the way, is the technology which is used almost everywhere. Now, laser enrichment is a newer technology which is even cheaper, energy cost is extremely low. Here a tunable laser excites and ionizes the uranium 235 in the initial supplied mixture, and then used to separate the uranium 235 from uranium 233 using a magnetic field. So, I do not want to discuss much about this laser enrichment, because it is something still under research and yet to go for any kind of commercial application. After this separation process is done, following any one of them, gas centrifuge being the most common one, enriched UF6 gas is allowed to liquefy and then solidify in the cylinders, and then we of course can't supply the UF6 directly as the fuel in the nuclear reactor, because the temperature UF6 can survive up to is not sufficient for that. At such high pressure and temperature conditions inside a nuclear reactor, UF6 will not be able to sustain, and so we have to convert this UF6 back to UO2. But remember that that we are talking about is now an enriched one, that is more number of UF6 molecules will comprise U235 than U238 or than originally we had, and then this conversion to UO2 is done, which is generally a solid material or a powdery kind of material. It is therefore pressed and sintered at around 1400 degrees Celsius to form fuel pellets. Pellets can be of rectangular block shaped or cylindrical shaped, like we have talked about earlier. This 1400 degrees Celsius up to which we need to sinter this UO2 is too high for UF6, and that is why we do not use UF6 directly as the fuel. Now, first in the fuel cycle, the first one we can have, first kind of operation is the open fuel cycle, where this natural uranium, after going through this conversion, enrichment and uranium oxide fabrication, is supplied to a thermal reactor, and whatever comes out of the thermal reactor, that is just thrown away as the spent fuel. Therefore, to produce a thermal power of 1500 gigawatt using this thermal reactor, we need something like this amount, 306,000 megaton or metric ton of uranium over a period of 1 year, and 29.864 thousand of MTHM per year becomes waste or goes for waste. Here this unit MTHM refers to metric ton of heavy metal. That is, we are not talking about uranium oxide mass, rather we are talking about the mass of this metal part, that is uranium part only. Initially we have supplied 306,000 natural uranium, but we are getting nearly 10% of that as the final spent fuel. So, which is quite large. And also the spent fuel that comes out, that still contains about 96% of the original uranium, out of which the U235 content can be less than 1%, and also there can be 1% of plutonium, and rest about 3% used for the used fuel comprising waste products, which can further go for processing. The step after this conversion, or often after the power production, is the reprocessing, in order to harness the fuel, whatever fuel left in the spent portion, we go through the reprocessing process. Here the uranium and plutonium are separated from the waste product by first chopping up the fuel rods and dissolving them into an acid to separate the various products. The recycling of uranium and plutonium into the fresh fuel produces a significant reduction in the total amount of waste. So, whatever total amount of waste that we are getting, if there is no recycling, then that will also contain all this unburned uranium or plutonium, or I should not say unburned, it is that portion of uranium and plutonium which does not participate in the reaction, and if we can somehow separate them out, then it can be mixed with the fresh fuel and can again go back to the reactor. So, about a significant amount of this waste can be saved. Of course, about 3% of the total mass contains high level radioactive wastes, which need to be stored in liquid form and subsequently solidify. For the standard procedure that is followed for spent fuel reprocessing, it is called PUREX, plutonium uranium redox extraction. It is a standard aqueous nuclear processing method for the recovery of uranium and plutonium from the used nuclear fuel. It was proposed by Anderson and Asprey at the Metallurgical Laboratory of the University of Chicago as a part of the Manhattan Project. It was done around 1947. This is a standard chart of reprocessing. The unused fuel or the spent fuel from here, that is taken to the shearing or dissolving unit, where they are, like I mentioned in the previous slide, they are chopped into smaller units. The cladding is also removed from this. This metal chips refer to the cladding material, and then which is going out here, and then whatever is left, those uranium and plutonium, they go for the separation stage, where the fission products are separated and only uranium and plutonium that remains. So, this is the step where plutonium, the fission products, all those long living fission products are separated out from the uranium and plutonium, that is the remaining fuel. The fission products which are separated in this block, they are then stored in suitable containers and goes for long term storage. We shall be discussing about the process of this fuel storage, or I should say the storage of the waste product in our last module. But the uranium and plutonium that we have, that goes for purification, where they are also separated from each other, generally using some kind of chemical procedure. Then we can have two ways. Generally nitric acid plays a big role in these all chemical reactions that we are having. So, denitration is the process of removing the nitrate part from the fuel compound that we are having, and before we go for the final product storage, we can generally go for two kinds of option. One is storing pure uranium oxide, other is storing the uranium plutonium mixed oxide, or the so called MOX. The role of MOX is somewhat similar to the enrichment, because the objective of enrichment is to increase the U-235 percentage total fuel, or I should say the increase in the fraction of fissile nucleus in the total fuel. And if we go for a MOX, that effect is also similar, because plutonium itself is radioactive, or I should say it has a high fission cross section, and therefore, adding plutonium into uranium, that will also lead to a increase in the fraction of fissile nucleus in the total compound mixture. So, this is a very rough diagram. Instead of going to the detail, here you can identify what are the possible steps during this reprocessing. Reprocessing very important role in nuclear industry, because only through this reprocessing step we can recover a significant portion of uranium and plutonium from the spent fuel. If this step had not done, then all those uranium and plutonium would have been lost to the waste product. If we see the global inventory of separated recyclable material, the values for uranium and plutonium, these are given here, but natural uranium equivalent, that is the 5,000 of uranium that we can reprocess, or we can get from the reprocessed fuel, is equivalent to 50,000 tons of natural uranium. And very interestingly, if we can get 320 tons of plutonium from the reprocessed fuels, it is equivalent to 60,000 tons of natural uranium, because of its much higher burn up. And the corresponding saving in natural uranium requirement is shown in this particular table. In 2015, it is only a projection starting from 2015, total amount of enriched and reprocessed uranium comes to be something like this, and use of plutonium or plutonium used in MOX is something in this. So, the total uranium, natural uranium replaced can be 1720 tons. That is, in 2015 we have received about 820 tons of enriched uranium and 900 tons of plutonium has been gone to fabricate these MOOCs. So, a total 1720 tons of uranium, natural uranium has been replaced by this. There are several other countries or several countries where this process is also going on, this reprocessing, that is, where for LWR, that is LWR type of fuel, where like PWR, BWR, etc. and these are the common facilities that we have, whereas other nuclear fuels are being tried in here. Here the role of India is also important. In India, PHWR is the primary kind of reactor which uses heavy water as both moderator and coolant, and we can see from this about 330 tons of material or uranium can be recovered per year from these 4 PHWR plants. So, a total of 5370 tons per year of fuel can be saved. So, the closed fuel cycle is the one which makes use of these MOOCs. You can see the natural uranium is supplied here, which gets converted to the uranium oxide during the enrichment process, after enrichment I should say, which goes to a thermal reactor which is producing this amount of energy, but the spent fuel from the thermal reactor goes through this reprocessing process like pyro process, and also the MOOCs fabrication. This MOOCs is supplied to the first reactor to get 685 gigawatt of energy. So, if we add this if we add this 815 gigawatt with 685 gigawatt, we get the total 1500 megawatt of power, but this will lead to a significant reduction in the total fuel consumption because we are using MOOCs. And finally, the waste product that we are getting, I would urge you to compare the values with the what we got in the previous one. This is the mixed or hybrid fuel cycle, where the thermal reactor itself is of capacity 1500 gigawatt, but it is receiving both a fresh stock of uranium oxide and also a fresh stock of MOOCs from the MOOCs fabrication plant. So, both are supplied to the thermal reactor, and finally, this amount of MOOCs will not be spent, that is, this comes out from the reactor. All these 3 models have its own advantages and disadvantages, but generally the closed fuel cycle or hybrid fuel cycle are more preferred in modern day generation 3 or generation 4 reactors. Now, let us come back to the fast breeder reactors. Our discussion started with fast breeder reactors, but we have discussed about the concept of breeding in the previous lecture, and here so far we have talked mostly about fuel and fuel processing. Let us quickly check what can be the characteristics of fast breeder reactor, which I am sure all of you can guess by now. Significant excess of neutrons because of very low parasitic absorption. There is no moderator inside this, and coolant can be a liquid metal coolant whose parasitic absorption generally is quite low. So, high enrichment is generally required as there is no moderation, and so the neutrons will not be able to come to the thermal neutron level, and for fast neutron level their absorption cross sections are quite low. So, we need a large enrichment in order to provide more sites for interaction between neutron and nucleus. Then much more compact reactor core to attain required level of reactivity. The total size of the critical mass requirement for a given power output generally is smaller for these fast breeder reactors, and therefore, core size needs to be much smaller. Power density reasonably high. System pressure is low, they can work more or less at the atmospheric pressure itself, and the thermal conductivity showed by the coolant. Thermal conductivity for the coolant has to be very high, as because of this high energy density only, and that is the reason to go for liquid metals. Metal or ceramic fuels are used with metal cladding. Now, we are in a position to compare the fast breeder reactors and PWRs. If we go point by point, in case of PWRs we use only slightly enriched fuel 3 to 5%, whereas in FBR we go for very high level of enrichment 15 to 20%. The moderator in PWRs is water. No moderator required in case of fast breeder reactors, because we want to operate with the fast reactor itself. Heat transfer happens to the water because water is the coolant in PWRs, but for breeder reactors we have liquid metal or metal alloys acting as the coolant. Breeder reactor also works at a low pressure, but the pressure is high for the PWRs, something in the range of 70 bar. And also breeder reactor, by definition they are able to breed newer nucleus, and their total number of nucleus that has been developed through the breeding is replaced with this 1.2 number of fissile isotopes. But there is no such kind of provision in PWRs. The fissile materials are consumed and corresponding replacement with plutonium is extremely small. What are the pros and cons of fast breeder reactors? Of course, improved neutron economy, because it can give much higher power output corresponding to a given neutron flask. It can recycle the nuclear waste, on which we have had lots of discussion so far. It can produce fuel for thermal reactors, like the doubling time is something that refers to doubling in the number of total fissionable nucleus. Now, when doubling time has been attained, that reactor or excess waste fuels can be taken out, can be reprocessed slightly. Those waste product can be taken out and can be processed slightly, and in course of doubling time it will produce the same number of new fuels as it was originally had. So, that new fuel can be used to start a new thermal reactor. Then liquid metal has much better heat transfer characteristics compared to water, which is advantageous. No pressure vessel, that is another big advantage also. But there are also disadvantages, like superior control systems are required, the fuel being highly enriched. So, control should be optimum. In certain situation, a fast breeder reactor can have positive reactivity effect from void coefficient. The void reactivity effect or temperature reactivity has to be negative as per definition. The handling of liquid metal is also not easy. They are heavy, they are corrosive, and they are generally electrically conducting as well. Therefore, special technology and handling is required. FBR can be expensive compared to PWRs. And one final point, the knowledge of FBR is still not as widespread as like PWRs or BWRs. Only very few countries, just 4 or 5 countries, are presently having active fast breeder reactor plants in their kitty, and the technology that they apply there or employ there, that those are also not publicly available. So, we need to know more, need to understand more about, before going for common, we need to know more, we need to discuss more about possible kinds of ways we can control a reactor, and at the design step itself everything should be proper, and that can come only through rigorous research and experimentation at laboratories. This is one sodium cooled fast breeder reactor. You can clearly see here you have a big pool of sodium, the core is immersed into this, and this intermediate heat exchanger is also immersed in this big pool of sodium. So, the energy released by fission is absorbed by this coolant, which passes through this line going through the steam generator. In the steam generator, the water is allowed to receive the heat from this hot sodium, thereby getting converted to steam, and that steam can be utilized in turbines and generators. This is another type of design, which is the late cooled fast reactor, where the working medium can be generally is a gaseous one, and the working medium passes through a gas turbine, then it can go through steps of or stages of recuperator and compressor and heat sink. So, both this late cooled fast breeder reactor and the sodium cooled fast reactor, they are under the generation 4 initiative, and so none of them have any active plant at the moment. Finally, is the pool and loop type design. Nuclear reactor, as the two diagrams that we have seen, if you look carefully, their figures are looking quite different, and accordingly fast breeder reactors can have two kinds of designs. One is the pool type design, other is a loop type design. The sodium cooled fast reactor that you have seen, that actually adopts the left one, that is a pool type design. In case of pool type design, we have a large pool of liquid sodium, and the reactor core, the pump which is this one, and also the intermediate heat exchanger like this one, all are immersed into the pool itself. Liquid sodium is pumped by this pump to pass through the reactor core, from where it gets the energy and then it enters this intermediate heat exchanger. Through the intermediate heat exchanger, while passing through the intermediate heat exchanger, it is also in indirect contact with the intermediate while passing through this intermediate heat exchanger, liquid sodium transfers its energy to another line where the secondary side we have steam or water. This water boils to produce the steam. Sorry, I am wrong. Actually, I would like to correct here. This intermediate loop is also having sodium as its working fluid. So, I am drawing again the sodium which is coming from the core here with high temperature, while passing through this intermediate loop, that passes its energy to another stream of sodium, which in turn goes to this second heat exchanger and transfers this energy to the water which is entering this from here. So, steam comes out which can be supplied to the turbines. But in case of loop type design, here this pump and intermediate heat exchangers are outside the liquid pool. The core is still immersed into the pool, but the pump is outside, which forces the liquid sodium to pass through the core and then enter through this line to the intermediate heat exchanger. Intermediate heat exchanger, the sodium in the intermediate heat exchanger transfers heat to another stream of sodium and then goes to the steam generator like in the previous case. So, in case of pool type design, we have core, intermediate heat exchanger and the sodium pump all immersed into a pool of liquid sodium, whereas in case of loop type design, it is only the core which is immersed into liquid sodium, the intermediate heat exchanger and the pump are outside. Both designs have their own structural advantages and disadvantages. While the pool type design is mostly preferred in USA, the loop type design is more popular in European countries. And also the designs that you have seen in the previous slide, if we just go back, this is a sodium cooled first reactor. You can clearly see this is the core, this is the pump and this is the intermediate heat exchanger, and they all are immersed into this pool of liquid. So, this is a pool type design, and then this sodium is going to this sodium is transferring its energy to this second stream of sodium, liquid sodium, and that in turn is supplying its energy in this steam generator to this stream of water which is coming via this line. So, this is a pool type design. But if you see this late cooled first reactor, here the reactor core is immersed, but this heat exchangers are kept separately, and it is definitely not a loop type design, but it is also not a proper classical pool type design as well, or loop, because here the reactor core and the heat exchangers are kept in separate blocks. So, modern generation 4 designs are sometimes trying some kind of combination between pool and loop type in order to take advantage from both of them. So, today's lecture is up to this. I have one more lecture left on this fast breeder reactor, where I shall be talking about a few other relevant aspects of this fast breeder reactor. So, whatever queries you have, please keep on sending the mails, and I shall try my best to give or respond to your queries immediately. So, thanks for the day. Bye.